Welcome to my lab for Oscillations. The objective of this lab was to examine the motion of a spring mass system, to create a computer model that predicts this motion, and then to determine if the energy principle is satisfied in this system. The results of this lab will be shown in the next two graphs. This graph is a plot of the observed position data, shown by the red line, and the predicted position data of the model, shown by the blue line. This data is very similar and shows that the model was very successful in predicting the motion of the system. This is an energy graph of the system. We will explain this more in depth later, but the key point of this graph is shown by the yellow line, which shows that the total energy of the system is equal to 0, meaning that the energy principle was indeed satisfied. In this lab, we use Hooke's law to calculate the force of the spring, and we assume that the net force is equal to the force of gravity plus the force of the spring. Also, Newton's second law, shown on the last line, is used inside our computer model to help us predict the position of the spring. Also, our simulation operates under the energy principle, which assumes that no energy is lost or gained by the system. The equations for calculating the energy principle are given here, where gravitational potential energy is calculated as mass times gravity times the change in height. Spring potential energy is calculated as 1/2 times the spring constant times the stretch squared. Kinetic energy is equal to 1/2 times mass times velocity squared, and total energy is simply equal to the kinetic energy plus the gravitational potential energy plus the spring potential energy. The first step in this lab is to load the given video into Tracker to extract the position of it. As you can see here, the origin has been placed at the attachment point of the spring, with the positive y direction going up and the positive x direction going to the right. The video was calibrated with the given stretch length of the spring, which was 0.7 meters. As we play the video, we can see that the position of the spring has been tracked, and its x and y positions have been recorded in the table to the right. As we can see here, this top graph shows the oscillations of the spring in the x direction, while this lower graph shows the oscillations of the spring in the y direction. We now move over to our Python code to take a look at how our model was created. The first step is inputting the given data, which was the ball's mass, 0.402 kilograms, and the spring constant, which was 6.83 newtons over meters. Using Hooke's law, which was shown earlier, in the given stretched length of the spring, the relaxed length of the spring was calculated to be 0.123 meters. We can see here that the kinetic energy, the gravitational potential energy, and the spring potential energy have been set to their respective equations, which were shown earlier. Also, Newton's second law has been input in this while loop of the code, which updates the position of the spring as time goes on. When we run the code, this is what we see. The predicted motion of the spring is shown by the blue line, while the actual motion is shown by the red line. The blue arrow represents the spring force, while the black arrow represents the gravitational force acting on the spring. Also note that the model produces this energy graph of the system, which was shown earlier. If we alter just a few lines of our code, we can get our model to produce a graph of both the observed motion data and the predicted motion data, which was also seen earlier. As we take a closer look at the graph of the energies, there are several key things to note. First, note how the gravitational potential energy and spring potential energy are similar in size, but simply opposite in direction, as when one oscillates positively, the other oscillates negatively. Also notice how the kinetic energy oscillates positively and negatively. This makes sense, as when the spring changes direction, its kinetic energy is momentarily 0. Most important, however, is the yellow line, which shows the total energy of the system. This line is equal to 0, showing that no energy is lost or gained by the system, and the energy principle is satisfied. Now, it is important to consider the oscillation periods of the spring, which is simply the time it takes for the spring to make a full range of motion. Using the equation shown, these have been calculated as 1.638 seconds in the x direction and 1.397 seconds in the y direction. Because it takes less time for the spring to make a full range of motion in the y direction than it does in the x direction, this tells us that the spring either moved a shorter distance in the y direction than it did the x, that it moved with a faster velocity in the y direction than it did the x, or some combination of the two.